Okay, we're going to continue on with section 21.7, the transformer. Let's share the PowerPoint. And sometimes it is necessary to change a small AC voltage to a larger one or vice versa. We can do that using a device called a transformer. The figure shows the simplest form of an AC transformer, which consists of two coils of wire wound around a core of soft iron. Oh, I lost it. The coil on the left, which is connected to the input AC voltage source and has N1 turns, is called the primary winding, or the primary. The coil on the right, which is connected to a resistor R and consists of N2 turns, is the secondary. The common iron core is used to increase the magnetic flux and to provide a medium in which nearly all the flux through one coil passes through the other. When an AC voltage delta V1 is applied to the primary, the induced voltage across it is given by the equation shown here. V1 equals minus N1 delta VB divided by delta T. You should be familiar with that equation. Let's assume that no flux leaks from the iron core. So the flux through each turn of the primary equals the flux through each turn of the secondary. That means the voltage across the secondary coil is given by this equation. V2 equals minus N2, the change in flux over the change in time. If we combine the two equations, we get this one. V2 equals, notice the ratio of the turns, N2 over N1 times delta V1. When N2 is greater than N1, delta V2 exceeds delta V1, and the transformer is referred to as a step-up transformer. When N2 is less than N1, making delta V2 less than delta V1, we have a step-down transformer. Remember Faraday's law? It tells us that its voltage is generated across the secondary only when there is a change in the number of flux lines passing through the secondary. In that case, the input current in the primary must change with time, which is exactly what happens when an alternating current is used. When the input at the primary is a direct current, a voltage output across at the secondary a voltage output occurs at the secondary only at the instant a switch in the primary circuit is opened or closed. Once the current in the primary reaches a steady value, the output voltage at the secondary is zero. You might be thinking that a transformer is a device in which it is possible to get something for nothing. For example, a step-up transformer can change an input voltage from, say, 10 volts to 100 volts. This means that each coulomb of charge leaving the secondary has 100 joules of energy, whereas each coulomb of charge entering the primary has only 10 joules of energy. That's not the case, however, because the power input to the primary equals the power output of the secondary. I1 delta V1 equals I2 delta V2. Although the voltage at the secondary may be, say, 10 times greater than the voltage at the primary, the current in the secondary will be smaller than the primary's current by a factor of 10. This equation assumes an ideal transformer in which there are no power losses between the primary and the secondary. Real transformers typically have power efficiencies ranging from 90% to 99%. Power losses occur because of such factors as eddy currents induced in the iron core of the transformer, which dissipate energy in the form of I squared R losses. When electric power is transmitted over large distances, it's economical to use a high voltage and a low current because the power loss from the resistive heating in the transmission lines varies as I squared R. If a utility company can reduce the current by a factor of 10, for example, the power loss is reduced by a factor of 100. In practice, the voltage is stepped up around 230,000 volts at the generating station, then stepped down to around 20,000 volts at a distribution station, and finally stepped down to 120 volts at the customer's utility pole. The transformers are not only used for step up and step down. They're also used for isolation, where the unit being powered can't be connected to any type of ground. That's a unusual case, but it is used. We used to use it all the time. So this ends the transformer section. The next section we will discuss are sections 21.8 and 21.9 in one video, Maxwell's predictions and Hertz's confirmation of Maxwell's prediction.